let's have a look at this example. It says, show that a root of the function f of x is x cubed minus 2 occurs between 1 and 2, understanding the x values. So graphically, it's suggesting, here's our x-axis, at 1 and then at 2, somewhere between 1 and 2, the graph either does that, or between 1 and 2, the graph might do that. And that indicates a root has occurred. So what do we know in this case? We know here, if it is this situation, we'll know that f of 1, when x is equal to 1, we'll get a negative, and then the function value at 2 will be a positive. Or if we get that the function at 1 is a positive number, we should get then that the function at 2 is a negative. So simply, to show that a root occurs between 1 and 2, we find f of 1. f of 1, sub 1 in for x, 1 cubed minus 2, which is 1 minus 2, which is negative. That's the most important thing. I mean, I know that it's not a difficult calculation, but if it involved decimals or anything, we would just compare the two and say, well, is it going to be positive, is it going to be negative? That's all we have to establish. Then, let's have a look at what's happening when we get to 2. So, it's possibly this situation here, because f of 1 is less than 0, it's a negative, the y value is a negative. At f of 2, we'll have 2 cubed minus 2, 2 to the 4, 8, minus 2 is 6, which is overwhelmingly positive. So it is definitely this situation. So we know that the y values have gone from a negative value to a positive value, therefore a root occurs between 1 and 2. Part 2 says, using the halving the interval method, use the halving the interval method to show that the solution is between 1.375 and 1.125. Okay, well, we could simply do function value at 1.5. So, because that's halfway between 1 and 2. Halving it exactly in half. What is the function value at, is it a positive or is it a negative? So we've got cubed minus 2 is 1.375, which is clearly a positive value. So, just zooming in on this part of the graph now, between 1 and 2, we've got 1.5, and what we've established here in this really simple calculation is that at 1.5 we are above the axis. So what do we know? We know that there must be a root somewhere now between 1 and 1.5. So our next trial is at halfway between 1 and 1.5, which is now we'll try 1.25. So we put 1.25 into our calculation, and you can see there on the calculator we're now getting a negative answer. At 1.25 the value was negative, so we've now come at 1.25, we're down here. So again, we know this is 1.25, we halve the interval. We're going halfway between 1.25 and 1.5. Halfway between there is halfway between is 1.375. How did I get that? Add the two values, your 1.25 and your 1.5, so we want to be in between here. Add those two together and halve them, you get your 1.375. When we put that into the calculator and subtract 2, we're finding the function value now halfway along. halfway between this interval, it's saying the function value is back positive. Now, if we zoom in on just this interval here, between 1.25 and 1.5, we know at 1.5 it's positive, at 1.25 the function value was negative, and what we've just established here is at 1.375 you get a positive value, which means we're back up here. So what do we know now? We know that there must be a root between 1.25 and 1.375. I think that was the question. Establish that there is a root between 1.375 and 1.25, and we've done that by halving the interval, trial and error, readjusting the interval depending on the result of the function values, whether they're positive or negative. You could get started, I think, now with exercise 6e. If you are wanting to see the solution to this example, was found under inverse functions, but it's not really about inverse functions. It's show that there is a solution between these two values, and then by halving the interval. It's really more about halving the interval. It's actually in the notes under the tab Student Notes. I'll just write the solution up and I'm sure you'll be able to follow it. You don't need to listen to a video to have this solution.